Cosmic bombshell. The truth about Andromeda's signals. For decades, we've treated Andromeda like the quiet kid next door. You know, pretty to look at, always there, but never really interrupting the cosmic conversation. It just hung in our sky like a beautiful static painting. Then, without so much as a polite cough, it started shouting. And not just a little yell, we're talking millisecond-long radio flashes. Thousands of times brighter than anything our own Milky Way casually produces, now spilling out of M31. These aren't your garden variety pulsars, they shrug off magnetars with disdain. And they arrive so incredibly fast that your brain literally finishes one heartbeat before the pulse itself has vanished forever. Something utterly phenomenal in that trillion-star city is firing off cosmic bullets of light, and for the very first time, we can't comfortably blame a star we already know. This isn't just a blip, it's a bombshell, forcing us to rewrite the rules of what galaxies can do. The first blip on the radar. Our cosmic detective story really kicks off in 2022. That's when the Very Large Array's real fast system, a mouthful I know, but incredibly powerful, was diligently hunting for fast radio bursts, or FRBs. These are those enigmatic, millisecond-long chirps that have been popping up all over the sky, baffling astronomers for years. Two of them, cryptically named 2023-0506C and 2023-03A, did something particularly interesting. They passed straight through Andromeda's line of sight. At first glance, that might sound routine, right? FRBs pierce galactic halos all the time. It's just how they roll. But here's where it gets weird. When astronomers calculated the dispersion measure, that's the scientific term for the smearing effect free electrons impose on radio waves as they travel through space, the numbers absolutely refuse to add up. Think of it like this. A radio pulse is a perfectly sharp beep when it starts. But as it travels through space, encountering free electrons, it gets stretched out, turning that sharp beep into more of a downward slide, like a record slowing down. The more electrons, the more smearing, the bigger the slide. The halo of Andromeda, it turns out, is injecting far, far more delay than any of our simulations predicted. This implies a searing, invisible cocoon of plasma wrapped around the galaxy, far denser and more extensive than we previously imagined. In plain English, our closest galactic neighbor isn't just photogenic. It's electrified, shrouded in a colossal superheated atmosphere. This finding provides indirect evidence of a hot baryonic halo around Andromeda, aligning with theoretical models of how galaxies hold onto their gas, but at a scale that's really making us scratch our heads. Why these pulses are weird. Now let's be honest, FRBs aren't front-page news on their own anymore. We've detected hundreds of them, traced a handful to galaxies billions of light years away, and even nailed one to a magnetar right in our own cosmic backyard. We're getting pretty good at finding them. But what makes these Andromeda bursts so genuinely awkward, so utterly fascinating, is the context. See, normal FRBs typically come from one of two places. Either young, incredibly active star-forming regions bursting with stellar nurseries, or the chaotic, violent suburbs of giant black holes, where things get messy fast. Andromeda, however, doesn't quite fit that bill. Its star-forming belt is, well, modest. Not exactly a hotbed of cosmic fireworks. And its central black hole, while massive, is remarkably quiet, almost serene, compared to some of its more boisterous cousins. Yet, these pulses are brighter at 1.4 gigahertz than virtually anything else we can detect inside the entire galaxy. If they truly originated within M31 from something we understand, we should absolutely see an afterglow, maybe a glowing cloud of shocked gas, some lingering wreckage from a cataclysmic event. Instead, the trail ends as abruptly as a light switch flicking off. That unsettling absence of wreckage screams new physics, or at the very least a new, previously unknown address for physics we thought we understood. It suggests a diversity in FRB subpopulations and complex origins that we're only just beginning to grasp. A crash course in galactic halo CSI. Okay, let's get a clearer picture of what's happening here. Imagine a radio pulse, born far beyond Andromeda, perhaps from a neutron star merger or a flaring blazar, hurtling towards us. To reach our telescopes, it has to slog through two incredibly dense battlefields. First, there's the vast expanse of intergalactic space, a relatively sparse but still electron-filled void. Then, it hits Andromeda's own halo. This halo isn't just empty space. It's the galaxy's atmosphere, only it's made of million-degree plasma, laced with invisible, tangled strands of magnetic spaghetti. Every single free electron along that path stretches the pulse, turning that sharp beep into a downward slide, a delayed signal. By meticulously measuring exactly how far that signal slides, astronomers can, quite literally, weigh the halo. It's like cosmic sonar, pinging the hidden bulk into view. The latest tally suggests that Andromeda shelters at least 10 billion solar masses of superheated gas. That's enough material to build 50 Milky Way-sized nebulae. We never really saw this stuff before because it glows mainly in X-rays that are often too faint for most telescopes to detect directly. But these FRBs act like powerful cosmic searchlights, illuminating this massive, previously hidden reservoir of baryonic matter. This is huge because it helps us understand the missing baryon problem, where all the normal matter in the universe actually is. These FRBs aren't just mysterious signals. They're our new, invaluable tool for mapping the invisible architecture of galaxies. Could a magnetar inside M31 be the culprit? It's a compelling idea. Magnetars are ultramagnetic neutron stars, incredibly dense stellar remnants that occasionally crack open in colossal starquakes, releasing flares so powerful they can be detected across the entire universe. Many FRBs are, in fact, attributed to these cosmic heavyweights. The problem is, we've already scoped Andromeda for magnetar X-ray flashes, and we've consistently come up empty. A magnetar bright enough to spit out an FRB of this magnitude would also be expected to belch out significant X-rays during its energetic outbursts. Yet Swift's All-Sky Monitor, a highly sensitive instrument designed to catch these very events, records only a gentle murmur from Andromeda's core, nothing like the telltale X-ray signature of a powerful magnetar eruption. Add to that the fact that repeated bursts have never been seen from the same sky pixel within Andromeda. Magnetars often produce repeating FRBs, sometimes in erratic patterns, but the same source tends to burst multiple times. This lack of repetition from a fixed point severely undermines the magnetar story for these particular Andromeda signals. We're left with two rather unpalatable choices. Either these are single-shot cataclysms, events so incredibly energetic they somehow outshine an entire galaxy in a millisecond, or they're powered by an entirely unknown engine capable of firing just once and then vanishing without a trace. Neither option is particularly comforting for astronomers who love tidy explanations. The alien elephant in the room. Okay, let's address it. Whenever nature gives us a signal that's this tidy, this precise, our first, most primal instinct is often to blame little green engineers. It's human nature, isn't it? The idea of an advanced civilization reaching out across the cosmic void is incredibly alluring. History, however, keeps that thought on a very short leash. When we talk about these pulses, there's no modulation, no discernible pattern, no information encoded within them. They arrive at seemingly random intervals, closer to a bolt of lightning than a structured language. More importantly, the energy budget required for such a feat is, frankly, biblical. To beam a detectable millisecond flash across 2.5 million light-years, you'd need to convert the mass of something like Mount Everest into pure radio waves in an instant. Think about that for a second. Any civilization capable of pulling off that kind of stunt would undoubtedly leave other, more obvious calling cards. We'd expect to see megastructures, colossal waste heat signatures, or at the very least, an anomalous infrared glow emanating from their home system. But Spitzer and Wise, our most sensitive infrared observatories, see nothing of the sort coming from Andromeda that fits this description. Until we find a pattern that absolutely cannot arise naturally, the alien hypothesis, while an intriguing pub conversation starter, remains just that, not a peer-reviewed conclusion. For now, the universe is just doing its magnificent, chaotic thing. Lessons from a chaotic past. Andromeda isn't just another pretty spiral galaxy, it's a cosmic cannibal with a violent, dramatic history. Roughly 5 billion years ago, it devoured a sister galaxy, leaving behind the compact nugget we now call M32, which many astronomers believe is the stripped core of that larger, unfortunate galaxy. This ancient merger didn't just create M32, it flung Andromeda's own spiral arms into asymmetric waves, permanently altering its structure. Hubble's deep surveys show us Andromeda's satellite galaxies orbiting backwards, tilted at rakish, impossible angles that completely mock our tidy computer models of galactic dynamics. This history of violence and chaos matters profoundly. Galactic mergers aren't just destructive, They reignite star formation, stir up powerful magnetic fields, and could, in principle, create rare but truly stupendous explosions, perhaps the stellar equivalent of a once-in-a-millennium supervolcano. Imagine the sheer energy released. If such an extreme event coincided with, say, the birth of a freshly formed black hole, or the collapse of an exotic quark star, we might just get a single blinding radio pulse, followed by profound, eternal radio silence. The chaotic environment, the ongoing gravitational interactions with its numerous satellites, and the remnants of past galactic collisions all contribute to a dynamic, unpredictable system where such singular, powerful events are perhaps more likely than we once thought. Andromeda's past isn't just history, it's actively shaping its present, and potentially, these mysterious signals. So, what's the next step in this cosmic detective story? Astronomers are now lobbying hard for precious time on the Square Kilometre Array, SKA. This isn't just any telescope. It's so incredibly sensitive it could theoretically pick up a mobile phone ping on Pluto. The goal isn't simply to catch more bursts, though that would be fantastic. It's to triangulate their origin to sub-arc-second precision. That's like pinpointing a grain of sand on a beach from orbit. If the next pulse comes from a globular cluster, for example, we'll start suspecting a rare type of compact binary system as the source. If it aligns perfectly with a dwarf satellite galaxy, we'll interrogate those star-forming clumps within it, looking for answers. And if, even with the SKA's incredible power, these pulses still refuse to repeat from a fixed point, we'll be forced to accept a truly profound reality: that the universe hosts one-shot cataclysms powerful enough to drown out an entire galaxy in a single millisecond. Either way, every new detection, every new data point, peels back another layer of Andromeda's electrified, enigmatic halo. It's turning our closest galactic neighbor into a living, breathing laboratory for cosmic catastrophes, a place where the universe's most extreme phenomena might be playing out right before our eyes. So, what's your bet? Is it an exotic starquake from a never-before-seen stellar remnant? A bizarre, unknown black hole interaction? Or is it something we simply haven't even begun to imagine yet? Drop your wildest theory in the comments below. The best idea gets pinned. If you want more cosmic detective stories that challenge everything you thought you knew, smash that subscribe button and ring the bell so you don't miss the next bombshell. For centuries, Andromeda hung in our sky like a painting, beautiful, static, silent. Today, it's transformed into a vibrant, enigmatic crime scene, littered with radio shrapnel, forcing us to rewrite the fundamental rules of what galaxies can truly do. Whether the culprit is a magnetar on steroids, a shredded star caught in a gravitational dance, or a phenomenon so utterly new that we haven't even named it yet, one thing is abundantly clear: the universe still has the boundless power to surprise us from just next door. So keep looking up, keep questioning, and keep that sense of wonder alive. Because the next millisecond flash could rewrite physics faster than you can blink.